Hi everyone, welcome back. Today I'll be introducing two fundamental data structures, stack and queue in Go. Unlike other languages, Golang does not have an inbuilt stack and queue class which you can call directly. In this video, we'll see how we can implement our own stack and queue with Go slices and also delve into detail how it works. In case you're new to my channel, I'm a software engineer, I've worked in Silicon Valley and specialize in Go. First, let's understand more about stacks. By definition, stack is a container of objects that are inserted and removed based on a last-in, first-out principle. Just like this tower of bricks, we can only add and remove elements from the top of the stack. Let's take a look at how to implement stacks in Go with slices. In case you're new to Golang, slices are basically Go's variation of arrays. While an array has a fixed size, a slice is a dynamically sliced, flexible view into the elements of an array. It consists of a pointer to an array, the length of the segment, and its capacity, which is the maximum length of the segment. To implement stacks with slices, we first create a slice in Go, and this can be done in two ways. The first way I'm showing currently, using the make function. This function takes in the type, in this case it's of integer, and the length, in our case it's 5, and an optional capacity. Now I'm currently showing the second way, and when called, make allocates an array and returns a slice that references to that array. Now that we have implemented stack with Go slices, let's implement the two operations that we can perform on the stack. First, push, which adds an element to the top of the stack, and pop, which removes an item from the top. Let's implement push, and for that, we can use Golang's append function, which has the signature as follows. For example, we can append an element to the end of the stack, and what this does is it adds elements to the end of the slice. In our case, since the capacity is already at 5, internally it will create a new array of size 6 and add the last element 1 to the end of the slice. Since the capacity is not enough, append actually allocates a new, sufficiently large slice that fits both the existing and new elements. So in our case, the length of the slice is updated to 6 and also its capacity. So depending on the implementation, append can operate in linear time, reallocating memory and copying everything on each append, or in amortized constant time. Now notice that with this, our top of the stack is actually the end of the slice. So to push, we just append the new element to the end of the slice. Now, let's implement pop. And to do that, we can just retrieve the last element of the slice, since recall, stack follows a last-in, first-out order. So that would be 1. And remember, we also need to update the stack with Go's syntax for reslicing as follows. So what we're doing here is we're actually slicing the stack up from and including index 0 up to but excluding the last index. Hence, we're removing the last element which we just popped. Internally in Go, the slice data structure and their relation to the underlying array is now changed, and the length would be updated to 5, but there is no change to the capacity. Notice that behind the scenes, slicing does not copy the slice's data or create a new array. It simply creates a new slice value that points to the original array. This is why slice operations are as efficient as manipulating array indices. Now that we understand how implementing stack with slices work in Go, let's take a look at some stack applications. Most importantly, stack is a recursive data structure. We can see why with the simplest application of reversing a word, in this case, cat. First, we push a given word into the stack letter by letter, starting with C, A, and then T. Now we pop it from the stack, and since stack follows a last-in, first-out order, T will be popped first, followed by A, and then C. So we have easily reversed a word with a stack. Now this recursive aspect will be important in computer programming algorithms like backtracking. This is a process which uses recursion to solve problems and requires us to access the most recent element in a series of elements. Think about a maze. How do we find a way out? Whenever we reach a dead end, we must backtrack. But backtrack to where? To the previous point where we made a choice. This means that each choice point, we're using a stack to store all possible choices. And backtracking just means popping the next choice from the stack. Now, popular algorithms like depth first search also uses backtracking to traverse a graph. On my channel, I've used the stack to implement DFS and solve LeetCode's jump game problem in Go. Check out the video linked above and in the description below if you're interested. Now, let's understand more about queue. By definition, a queue is a container of objects that are inserted and removed according to the first in, first out principle. Just like the name, we can think of a queue in programming like a literal queue in life. In a queue, only two operations are allowed. Firstly, onqueue, which means to insert an item at the back of the queue, or offer or add in Java, it's the same thing. Secondly, dequeue, which means removing an item from the front of the queue, or pull or remove in Java. We can see that the difference between stack and queue is in the removing. In the stack, we remove an item that is most recently added, while in the queue, we remove the item that was first added. Now let's take a look at how to implement queue using slices. Again, we need to first create a slice in Go, and this can be done using the make function. There are two ways to do that. We're currently showing the first way, and this is the second way. In both cases, in Go, we're creating an underlying array with a pointer to the array and return the slice. Now that we have queue implemented using slices, let's implement the two operations that we can perform. Firstly, onqueue. To implement onqueue, since we're adding elements to the back of the queue, we can also just use Golang's append function as introduced earlier. So now, we are appending the element 1 to the queue. Similarly as before, since our original underlying array's capacity is not big enough, Go internally creates a new array of size 6 and append the element 1 to the end of the slice. Then, internally Go updates the pointer to the new underlying array before returning it to the queue. Similarly, we're updating the length and capacity to 6. Next, to implement dequeue, we need to first retrieve the least recently added element. And in that case, it would be the first element because our front of the queue is actually at the start of the slice. And note here that we're just accessing the first element, which means it is kind of like peek in Java. Then, to pull or remove, we need to reslice the queue to exclude the first element we just examined. So we start from the first index up to and including the last index. With this, the length of our queue is also updated to 5. Now let's jump into some popular applications of a queue like the graph traversal algorithm depth first search. You can also check out my video where I use BFS to solve the LeetCode question linked above and in the description below. If you want more practice on your Golang skills, you can also explore my playlists for some LeetCode problems in Go. I personally think it's a great way to get introduced to the Golang syntax and be familiarized with Go. In this video, we've explored how to implement stacks and queue in Go and understood how the underlying slice operations work. I do plan on doing more videos about Golang tutorials and build some fun Golang projects. Subscribe if you want to learn more about Go programming and backend development. See you next time!